I'm Ryan Forsyth, he, him, his pronouns. I'm a software developer working on post-processing tools for E3SM. I'm going to talk about running and analyzing E3SM today with the water cycle group's approach to it. Can you advance the slide? Okay, so this is just an overview of the E3SM tools for every phase of model development, from model configuration to short-term archiving to long-term archiving, diagnostics, and analysis. So we're actually going to touch on pretty much every aspect of this today except for publication. So we have a brand new step-by-step guide that we've written in the past few months to really guide users through this process. Next slide, please. On Confluence, it's a living document, so it's easily changed to reflect changes in the process because we understand that things are going to change with how we run the model post-processing, so it can easily update with those. Confluence keeps a page history so you can see older versions. The summary box is on the right, and we're basically, this slide deck is going to go through each of these steps at a high-level overview. Obviously, the step-by-step guide goes through in more detailed instructions. Next slide, please. So the first part of the step-by-step guide is configuring of E3SM. So there's a run script that really handles all the logic, but really all you have to worry about is the parameters up at the top of that script that dictate how the logic flows. So for example, the case name, the branch of the code you're off of. So it's very easy to customize the run script by just changing a few of these parameters. Make sure all your changes are done within the script to keep provenance though. I do want to draw your attention to the bottom of this screenshot though, which is different predefined tests. So we have tests at for extra small to large scale, and then of course production for the full simulation. Next slide, please. So you do want to make sure to run some of those tests. You don't want to start your model on a Friday afternoon and come back on Monday and realize it crashed after an hour. So you can run these bit for bit tests to you can run these tests and check that everything works out bit for bit. The nightly test should check that, but it's good to double check. It just gives you greater confidence that your model will in fact run. So then once you have that confidence, you can submit the production simulation. So once that runs, next slide, please. So once it runs, you can look at the results. So there's a lot of results, tens of thousands of files or more. So you can do short-term archiving to help consolidate or organize that a bit more. So we have a screenshot of the subdirectory structure. So there's a subdirectory for each component of the model, atmosphere, coupler, etc. Also for logs and restart files. So this really helps organize the structure a bit more than what it is without the short-term archiving. Next slide, please. So in addition to the content of the results, you want to look at the performance information. So PACE is an excellent website for that. So all the jobs that finish end up on PACE, and it provides all sorts of major thing you want to look at is the model throughput. So for example, that's the 42 simulated years per day. Another cool feature is the chart on the right, which shows you how each processor is used and for how long. So for example, Ocean took so many nodes and ran for so long simultaneous with the atmosphere, whereas atmosphere ran on the same nodes as ice. And once everything's done, the coupler finishes. So this is a really handy way to sort of visualize what's going on with your run. Another thing that's noted in the step-by-step guide is how to resubmit a job after a crash. So you can look at the error logs, figure out what went wrong, and you can make a change, and the model will pick up from the last restart file. So you don't have to start from square one if your model ran, 100 years already. You can simply rerun it, and this guide has simple steps to follow to resubmit. Next slide, please. So zppy is a post-processing tool. It's brand new, just released in July, and it's a way to sort of run all the other post-processing tools. It's easy to customize the zppy run by just changing parameters in just a single configuration file. So far, zppy can launch jobs for various tasks, including NCO-generated climatology and time series, and various plotting capabilities, E3SM DAGs, MPath analysis, and overview global time series plots. Each job comes with a log file and a status file. So if there's any failures, you can rerun zppy on the same config file, and it will just rerun the jobs that previously failed. So you can fix them, and it will know what to rerun based on those status files. So it doesn't waste time recomputing things that already worked. Next slide, please. So this is just a little bit more detail on some of the tools I mentioned on the last slide. the different tasks that Zippy does. So one thing I want to draw your attention to is E3SM Unified, which is a conda environment that includes all these packages and many more. It's deployed on all the E3SM supported machines. Zippy is included in the latest E3SM Unified. Another important thing is that Zippy runs these packages in any environment you choose. So you can set that to be the unified environment, or you can customize it. So for example, if you have the latest E3SM DAGs that maybe isn't in the latest unified, you can customize Zippy to say you want the latest E3SM DAGs environment, but you can use unified on the other task. So it's very customizable. And we do hope to add more things to Zippy. So we hope to enable new sets. So for example, E3SM Diagnostics is always adding new sets to the package. So we'll add some of those, and then tools that aren't mentioned here yet, such as the ILAM package. So we do hope to add more and more functionality to Zippy in later versions. Next slide, please. So this slide looks a little complicated, but really it's just saying that Zippy takes information from the configuration file and bash Jinja2 templates to create jobs. And if it does look a little complicated, just remember that Zippy's doing all this under the hood, so you don't have to worry about what's going on. So all you have to do is set the configuration file on the left here. So this is a very abridged version, but it's very nice because Zippy allows inheritance. So on the left, we have a default section, and then we have tasks such as climatology, time series, and those can have subtasks. So for climatology here, we have monthly and diurnal, and then time series has various subtasks as well. So the nice thing is these can inherit features. So for the climatology subtask, we see that we have years set in the climatology task, so that can apply to both of them. So we're trying to post-process years 1 to 200 in 20-year chunks here. We don't have to duplicate specifying that. We can put that in the climatology task, and that applies to both subtasks. Similarly, the E3SM Unified set the latest and the default, so that will run for all of these. And if we wanted to run, for example, E3SM DAGs in a different environment, we could set that to be something different. We also have another parameter called environment commands to do further customization on that. So you could set that in E3SM DAGs, and that would override what's in the default section that everything else uses. So basically, the parameters set in the configuration file get combined with these template files, and then Zippy determines what jobs to run. So for the diurnal climatologies, that information goes with the climatology bash, and then we generate, Zippy realizes it needs to run years 1 to 20, 21 to 40, and so on, all the way to 181 to 200. And it does that with all these different subtasks. So time series, we have 4 subtasks, so that's 4 sets of jobs that get launched from it. And then at the bottom, we have various plotting capabilities, such as E3SM DAGs, MPAS analysis, and the global time series. These depend to some extent on the climatology and time series files. So how do we make sure that those get done first? Well, Zippy takes care of that. Next slide, please. So this chart, this graph shows some of the possible dependencies. So E3SM DAGs, a lot of the base functionality like the lat-long plots, the polar plots depend on climatology. The diurnal cycle diagnostics, however, needs the diurnal climatology. So you have, so if you set that, if you want that set to run, you can have Zippy depend on the climatology. And then also the time series, there's certain sets within E3SM DAGs like ENSO, QBO, area mean time series that require time series files. So if you set that, Zippy knows to create those as dependencies. Now you'll notice here there's 2 time series, years 1 to 10 and 11 to 20. In the config file on the last slide, we were doing time series in 10-year chunks instead of 20 like the climatology. So that's perfectly fine. Zippy will realize we need both of those time series jobs to get 20 years, whereas we only needed the 1 for climo. On the bottom, we have a little bit more complicated dependency graph. Global time series depends on the time series, of course, but also MPAS analysis. And MPAS analysis depends on earlier runs of MPAS analysis. So that final global time series for years 51 to 100 depends on the MPAS analysis for those years, which depends on the MPAS analysis for the years before that, and then of course the time series. So Zippy schedules all these jobs accordingly under the hood. The user doesn't have to worry about planning these dependencies. Okay, next slide, please. So after everything's post-processed with Zippy, you can document the model run, and you can get started on this while it's running even. But every model run or ensemble of runs should be documented on Confluence. There should be a single Confluence page that has everything you need to know about this run or ensemble. A key thing is listing all the job information, so that's what the screenshot is here. It lists the years that are run, the simulated years per day, and those hyperlinks should be links to pace. So again, failed jobs won't have a link for you to use, but you should still list it in the table. So this provides all the information about the various jobs that it took to run, do this model run. The page should also include the global time series plots and links to E3SM DAGs and MPAS analysis plots. So again, the Confluence page for a runner ensemble should have everything you need to know about that run. Next slide, please. Okay, so long-term archiving. So if a simulation is valuable, you probably want to keep it around for a long time. So to do that, you can use zstash, which is an HPSS long-term archiving solution built for E3SM. I've listed some key features here. I'll just go over at a high level. So files get archived into standard tars. The user can specify a maximum size. A big thing is that it creates checksums or computes checksums on the fly during archiving. Checksums are also computed for the tars. And those checksums are verified, are used to verify file integrity while extracting files. And the checksums and the metadata are stored in a SQLite database, which can enable faster retrieval of these files. So zstash can be used on multiple E3SM supported machines, not just NERSC with HPSS. So if you use it on a machine without HPSS, you can use Globus to transfer the files you've archived using zstash to NERSC HPSS. And then that way you have more permanent long-term storage archiving of the run. Okay, next slide, please. Okay, so we have a live demo scheduled after this, but I want to just say a few takeaways before we get into that. One is declarative, not imperative. So in programming languages, there's imperative languages where you say do this, then that, then that. But there's also declarative languages where you say, I want this done, I don't care how you do it. And that's really a key theme of the slides I've gone over today. For example, with the run script, you set the parameters in the beginning of the script. You're not changing the actual logic of the script. All you need to do is change those parameters, and that flows into the script. And it's the same thing with the zippy config file. All you need to do is set the parameters in the configuration file to say what you want post-processed, and Zippy handles the how. All the job dependencies, which jobs to launch. So if all those complicated charts, that's all under the hood. So Zippy does that for you. The other key takeaway is one-stop shop, everything you need in one place. So you've probably noticed that theme throughout the slides, which is just everything in one place for easy access. So the step-by-step guide provides detailed instructions on everything from first configuring the model to running it, to archiving it, to post-processing it. A model run's Confluence page should have all the information about that run, from job information on pace to the generated plots. And then Zippy automates multiple post-processing tasks. We're not quite at all yet, but we hope to add more and more with upcoming versions. So it's a one-stop post-processing shop. So yeah, those are the key takeaways. And with that, I think we should move on to the live demo of Zippy.
Okay, thank you very much, Ryan.
Thank you.
So let's try a live demo, see how that goes. I need to exit the full screen here. So I'm logged in on Chrysalis through the No Machine interface. If you don't use No Machine, I would strongly recommend that you give it a try. It makes life so much easier. So let's get started. So just for an example, I'm going to re-post process the 500 year of the V2 low-res PI control simulation. So we're going to launch post-processing script for the entire 500 year of that simulation at once. So the first thing we do, and I have some notes somewhere here so I don't forget the exact command. The first thing you do is you load the unified environment. This makes our life so much easier. Xala spends a lot of time several times a year to keep that going, but it makes everybody's lives so much easier. So I'm loading the most recent unified environment. And then I have a configuration file like Ryan described earlier. So let's go through some of it. As Ryan mentioned, you have sections and then you have subsection. And the first section is a default section that has some general declaration, including the input and the output directories. Typically, they would be the same. In this case, I'm redirecting the output to a different directory, test2, because I don't want to override the original post-processing I did for the original simulation. The good thing about having separate input and output is you could actually post-process somebody else's simulation. So if somebody ran a simulation and didn't have all the post-processing you wanted, you could actually post-process it yourself and save it under your directory. And then you also specify the path where the web files go, the partition where the job should be sent, and then the environment that should be used when running all the tasks. And as Ryan mentioned, this can be specified here in the default, in which case it applies everywhere, but you could also specify it in a task or in a subtask, and you could use a different environment if you wanted to test a new version of MPass analysis or E3SM diags. So the next section is the climatology. So we have a 500-year simulation. So I'm going to do climatologies every 50 years from 1 to 500. So 1 to 50, 50, 100, and so on, every 100 year, as well as every 250 years. So 1 to 250, and then there will be one going from 251 to 500. So you just specify the beginning, the end, and the increment that you'd like. And then ZP, we will do that and launch all the jobs. And then we have two types of atmospheric climatology: monthly mean regraded to 1 degree, and then monthly diurnal cycle also regraded. For this one, because it's very large data set, we only save one variable. For those, we save the default ones. Then we have some time series. Again, we're doing the full 500 year, and we're doing that in 50-year increment. We're doing atmosphere monthly, daily, atmosphere monthly, globally average, very handy for quick look plots, the land, and you could add other components. You could add rivers and other components. I think MPass will not work out of the box because they are a little bit different, but that could be implemented later if needed. E3SM diags, now we use the same year set as the climatologies we generated. There's a few other parameters that are used for comparison to observation, and then some parameters specific for E3SM diags. Then we have a few other tasks which are disabled here. EMWG is a user contributed task, so it's not supported, so don't try to use it. It's only for special cases. And then we have MPass analysis task here. MPass analysis takes a little bit of more time to run, so we redefine the wall time for the job from the default 2 hours to 6 hours. And then we run it every 100 years. The climatologies are always for 100 years, and the time series are cumulative. So the last MPass analysis job will cover 500-year time series and the last 100 year of climatologies. And the last task is the global time series, which provides those quick plot overview. And we'll just do it for the last, for the entire 500-year simulation. And it will reuse some of the info from MPass analysis from the last 100 year here. So you set up your configuration file. You see it's only 98 lines. It's pretty compact, even for a 500-year simulation. Typically, we post those configuration files on the simulation page, on the Confluence simulation page. So the easiest is to find one and then customize it. So once you have your configuration file, then the only thing left is you actually start ZP, and that's very easy. You just type ZP, and then you provide -C for the configuration file. And then from there on, ZP should be doing the work. So let's see what happens. So it says that the validation passed, and now it's going through the file, parsing it, and submitting all the batch jobs that are needed to complete the tasks that were required. We have climatology, monthly diurnal, time series, monthly atmosphere, And you see it's submitting one job for every 50 years, atmosphere daily, atmosphere monthly, globally average. Again, one job every 50 years because that's what we specified. Then the land, time series monthly. Now it's submitting the job for E3SM diags. So those jobs will have dependencies, so they won't start until all the climatologies are done. Now it's submitting the jobs for impasse analysis, and the last job being submitted is for the global time series. So now we can look at all the jobs I have in the queue. There you go. We can, so this, so I have like 100 jobs in the queue has been submitted to Chrysalis. And then we can go, you see, if you look at it, so we have some already running. You see some of the jobs are waiting, and you, by the name, you sort of see what the job is. Climatology, most of them are already running. Then we have time series waiting here, time series, and then if you scroll down enough here, the E3SM diags, you see they're also pending, but they show a dependency. So those jobs will not start until the jobs they depend on have completed successfully. And this is all, ZP sets up all the dependencies and passes them to Slurm, and then Slurm uses them when it executes. And then impasse analysis is the jobs are also waiting. We should have one already running, presumably up there. Yeah, here, the first impasse analysis is running, and then the later ones will wait until it's complete. So that's how you set up ZP, and this is how you launch it. And now you just wait a couple of hours, and you have 500 years of post-process at once, using lots of climatology, lots of time series, lots of plot sets with very little effort. Okay, I think we can stop here and take some questions.
Okay, thank you. Thank you both. I think without further delay, we can start the walkthrough for the results.
We just wanted a brief follow-up to show you what it looks like from the output of ZP. Initially, we thought about waiting a day and actually looking at the output, but we decided it might be more efficient if we run it also. I ran it earlier, 2 days earlier, and I have the output of the same configuration file, so we can look at that one. And I can walk you through some of those, some of what we see. So let me go. So today I saved the output under test 2. I did this exact same test a couple of days ago, and it's saved here. So under this, we have the case name. So the output from the other day's run, and then it creates a new subdirectory called post. So everything that is created by ZP is stored on the post, except for the web files, which are stored under the standard web directory. So if you have an issue, if everything is messed up, you can always go and just delete that subdirectory and restart from scratch. Then under post, you have a number of subdirectories. The first one I'm going to show you is the scripts directory. And that one includes quite a few files. And this is the tasks. So for each ZP task, we have a bash job. This is the actual job that was submitted to the Slurm queue. And then each job also has an output file. So this is the standard output and error, and then a status file, which is the file Ryan mentioned earlier, which tells you a brief summary of what happened. So we can look at what's in the status file. So if we do cat.status, star.status. Okay, and then you can see everything is okay. And we can count how many we have. So we had 97 jobs, and they're all okay. So all the 97 jobs that were submitted to post-process 500 years completed successfully. So that's the first level you can check. If something goes wrong, you'll get an error in one of the status files, and then you could look at the corresponding bash file to see if there is something obvious, or look at the output to see if you can understand what the error is. If you're trying to debug, you can also just resubmit directly the bash file to the queuing system. So you can just do a sbatch of this file and it will rerun, and you can actually iterate and progressively figure out what might not be working right. So we try to set it up so an average user can also understand failures, because that can happen. So this is the script directory. And then the actual output, we have component type of output. So let's go in atmosphere, for example. This is where we store the climatology and the time series files. At the top level, you have the grid information. So those output can be regrided. So under 180 times 360 is all the output that was regraded to 1x1 grid. Under GLB is all the time series that were globally average. You could also generate climatologies or time series on the native grid, in which case you would have a native subdirectory here. And let me just walk you through one of them. The regraded 1 degree. In there we have climatologies, monthly diurnal climatologies, and time series. On the climatology, we have them by year set. So we had specified 3 frequency, 50 year, 100 year, 250 years. So all the climatologies are in there. And then under time series, we have daily time series, monthly time series. So let's take a look at daily. And then we requested 50-year chunk. So they are all in one single directory. And we requested only a single variable, so we have only the precipitation in there, and each file is 50 year. So this is a time series of the 50 year. Okay, so then you have, let me go back up. Then you have similar directory, subdirectory for other components. And under analysis, we store results from actual analysis plot set. And I think right now we're only storing results from MPass analysis, because we use some caching for MPass analysis to reuse the data, so we store it there. This is to speed up the post-processing of long time series. We cache the results and we reuse them in subsequent runs. Again, if something goes wrong in MPass analysis, if the cache has a problem, if the dependencies are problematic, the best is you just go in and you delete the whole directory. You go into the scripts, you delete all the MPass analysis scripts, status file, and then you rerun ZP, and ZP will do and fill in all the gaps. The last thing I will show you is some of the web output. Let me find the link. Okay, so with no machine, you can open Firefox directly on Argonne. Okay. And then I saved the path because I never remember exactly where that is. So we save the output on the test, PI control, and then we have here the ZP tasks that produce web files are E3SM diags, global time series, and MPass analysis. Next to it, global time series just produces one plot, which is a quick overview of what happened or the 500-year simulation, net radiation, global mean surface temperature, ocean heat content, AMOC. Let me go back. Then MPass analysis, subdirectory, we have one entry for we did every 100 year. If we look at the last one, we have MPass analysis, and just to show you that we actually do have 500-year time series. And let's go pick up one time series here. global SST, for example, and it does go from year 1 to year 500. So everything was generated, all the dependencies were successful, and we get the last plot for 500 years. So that's, and then you have also in there, you also have an output for E3SM diags. So for E3SM diags, we have the option of plotting on different grids, so we save them separately. That could be useful if you do a high-res simulation where you want to run E3SM diags both on the regridded to low-res and regridded to high-res. You could do that. The output would not be clobbered. And then we have all the output. We have 15 year, 100 year, 250 year. And then let's look at the E3SM diags for 250 years. And for example, looking at precipitation, there you have it. So this is the V2 PI control precipitation average between year 251 to 500. This is the present day observation, and this is the difference. So everything worked with that one configuration file of about 100 lines. We were able to generate all this. I think it took less than a day. I think it took of the order of a couple of hours. That will depend, of course, how busy the machine is. But it doesn't take all that long, given that this was fairly large post-processing of 500 years. So I think we can stop here if there are any additional questions.